So today I want to go over something called the work energy theorem. And it's useful because it could ignore constant of force. And we could apply this no matter what the situation is. Unfortunately, we're going to bring back some old stuff to kind of help prove this equation and then kind of show how this is effective and not effective. So here's an example. Let's say we had a 5 kilogram block and we had a force acting on it. And this force, let's say, was 10 newtons. And this force would push this block 5 meters. So here's our situation. Force is pushing on a block of 5 kilograms, moves across at 5 meters. So if we look back, work is equal to force times distance. So our energy here is 10 times 5, so that is 50 joules. So we've added 50 joules of energy to this. Now I want to prove something to you that's pretty cool, is how this is related to motion. In order to do that, we need to bring back our old stuff. So VI, VF, A, T, D. Our goal is to find both VI and VF. VI is 0. I forgot to say, but let's say the thing starts at rest. And we want to know what this is and kind of show the connection between the two. Acceleration we can find because F is equal to M times A, sum of all forces. Kind of go back a little bit. Sum of all forces in the x direction is equal to, well, right now there's only one. We're not worried about friction, so it's just equal to force applied is equal to MA. So force applied is 10, mass is 5. So A in this case is 2 meters per second squared. All right, so acceleration is 2 meters per second squared. We have a distance of 5 meters, and then we can find VF. So we're gonna do that. So we have 1, 2, 3, 4. We're missing that one. So it's VF squared equals VI squared plus 2AD. And then we're gonna solve for VF. This is equal to 0. So it's just 2 times 2 times 5. VF squared. So VF is equal to the square root of 4 times 5, which is 20, plus or minus. So VF is equal to plus or minus, and I need to find my calculator. Square root of 20, which is 4.47. Okay. And what I want to show you is that the main goal is that work is equal to change in kinetic energy. That's what I want to show you. So now we have all the information to kind of prove that's true. We added 50 joules of work, and we have kinetic energy final minus kinetic energy initial. Initial was 0 because of that, but we could put it in 1/2 mv squared minus 1/2 mv squared. Initial final, this one is 0, so 50 joules should equal 1/2 the mass, which in this case was 5, times velocity 4.47 squared. Okay, and these should be equal, so let's find out. So this is equal to 20, remember. So 20 times 5 is 100, divided by 2 is 50. So we have that. Now what I'm going to do is I'm going to show you mathematically the same thing. So we have work is equal to force times displacement. Now for us, we could simplify this into MA. Like all force is equal to MA times D. So work is equal to MAD. Well, now we're going to kind of go through. We're going to assume a couple things, unfortunately. But this isn't true. This doesn't have to be true for all situations. And I'll kind of explain that at the very end. So we're assuming A is equal to constant in order so that we could use our equation VF squared equals VI squared plus 2AD. Because this kinematics equation is only valid if A is equal to is A is equal to constant. And why do I want that? I want to substitute this into here. So I'm going to rearrange this to VF minus VI squared divided by 2 is equal to AD, and you can substitute this in here. So you have work is equal to mass times this entity right here, which is VF squared minus VI squared divided by 2. And if you work that out, or distribute, so you have mass velocity final squared divided by 2 minus mass velocity I squared divided by 2. Rearrange it a little bit, 1/2 mvf squared minus 1/2 mvi squared. You have change in moment, or sorry, change in kinetic energy. So here is the work energy theorem. The change in kinetic energy will give you the amount of work, or the opposite, which makes more sense. If I'm inputting this much energy into an object, I'm going to change its kinetic so far. So if I say I gave you a push of so many joules, your change of kinetic energy is going to be defined by here. So this is a really cool tool, because even though we assumed A is equal to constant to get to show the mathematical part of it, this also works if force wasn't constant. So like before, where we talk about energy, we don't really care about what happens in between. All we care about is what we start with and what we end with. So as long as we know the initial velocity and the final velocity, we could find the work done on an object. It doesn't matter if it was constant, not constant, it doesn't matter. It's just work. So in real life situations where force is not constant, as long as we know the beginning and end, we could use this to solve our problems. And we could either say, okay, if we input this much amount of work, you're going to have this. Now, before I did say that if you had negative energy, that's not possible, because you can't owe nature energy. This is a little bit different. You can have negative work. You can have positive work, right? Negative work means that you have a negative change in kinetic energy. If you have positive work, that means you have a positive change in kinetic energy. Well, what does that mean? Well, remember, kinetic energy is final minus initial. So if initial is bigger, right, that will give you a negative work. So if initial is bigger and this is smaller, that tells you that if it's negative, this means it's slowing down. So if you take away energy, you're taking away kinetic energy, so it should slow down. If you're putting in energy, it should be faster. Okay? And that intuitively makes sense, right? If you add energy into a system, it's going to have more kinetic energy, which means it'll be a faster motion. So hopefully this makes sense. This is a really cool tool to have. Deriving it does require, once again, your old kinematics, but having this is actually pretty useful in these kind of things. So if you have negative work, that means you have negative change, slowing down, positive work, positive change, going faster, and you don't have to worry about what happens in between, whether it's constant or not constant acceleration. It works either way.